Hello, AP Calculus. We're going to talk today about L'Hopital's rule. This is actually a rule that can help us with limits. So just first, I want you to kind of remember some things we've done with limits before. When we are approaching a number, the easiest way to handle it was to just use direct substitution. So for example, on the very top one, the limit as x approaches 2, if you just plug 2 in for x, you would get 2 on the bottom, 2 on the top, the numerator, and 2 minus 2, which is 0 on the bottom. And whenever you get a number not 0, a non-zero number on top, but you get 0 on the bottom, that means the limit does not exist. Or on this one, this is x plus 3 in absolute value, and then x plus 31 on the bottom. We could use direct substitution, plug negative 3 on top, we get 0 on top, negative 3 on the bottom, we get 28. So 0 over 28 is 0. In a similar way on this last one, if we plug 0 in for x, we get 0 on top, 1 on the bottom, 0 over 1 is 1. So that is one way we can solve limits. We can also do limits as x approaches infinity. And if you remember, the shortcut with that is if the top has a bigger exponent, then the limit is infinity. So for example here, if you think about it, as x goes to infinity, the top goes to infinity because we got that x squared. The bottom just stays 5. So if the top is getting huge while the bottom is staying 5, the limit is going to be infinity because the top just keeps growing and growing and growing and growing while the bottom just stays 5. This one, where we have the limit as x approaches infinity, is the reverse situation because this time the numerator has a constant, 2, so it never changes, it just stays 2 all the time, whereas the bottom, x is getting bigger and bigger because x is approaching infinity. So in this one, it's the bottom of the fraction, the denominator, that is approaching infinity. And when that happens, the limit is 0. Which if you think about it, this number keeps getting bigger and bigger. So it's almost like thinking, well, 2 over 10, that's 0.2. 2 over 100, that's 0.02. 2 over 1,000, 0.002. It just keeps getting smaller and smaller. So when the denominator gets bigger and bigger, the whole fraction gets smaller and smaller. So this one will be a limit of 0 because the bottom is getting bigger. That's just a refresher on what we've done before. We come to problems like this. If you look at this one on top, we have the limit as x approaches 1. Well, if you plug 1 in on top, you get 0. If you plug 1 in on the bottom, you get 0. Now, we did talk about some ways we could solve this by factoring and canceling out. That still works. But there is another way, you'll see very soon, that might be even quicker. And then on this one on the bottom, the limit as x approaches infinity. This causes a problem because we are going to infinity on top and we're also going to infinity on the bottom. And there's nothing we can factor out, and there's no way to use the shortcut with exponents because we're not dealing with just polynomials. We've got a polynomial on top and an exponential on the bottom. So these create a problem because this one we get 0 over 0. We can't tell anything about that. This one we get infinity over infinity. And what both of those are called is actually indeterminate forms. So anytime you plug something in and you get 0 over 0, or you get any kind of infinity, positive or negative, over any kind of infinity, positive or negative, that's called an indeterminate form, meaning without doing something else, we cannot determine the limit in that form. And just to make sure it's clear with this infinity, it does not matter whether it's positive infinity over positive infinity, or positive infinity over negative infinity, or negative infinity over negative infinity. So the sign of the infinity doesn't matter. The point is, if the top is infinite and the bottom is infinite, it's indeterminate. Just so you know, in case you take more calculus classes in the future, there are other indeterminate forms and other ways we can go about solving them, but for AP Calculus, all we have to worry about is these two forms. And we're going to look at how L'Hopital's rule will actually help us solve these. As complex as it may seem, I promise you once you see some examples, you'll see this is pretty helpful and quick. Alright, so here's what L'Hopital figured out. When we're dealing with a rational function, so we've got two equations of x in a fraction, one on top, one on the bottom. It turns out if, so notice there's a condition here, hooray for conditions, assuming that if we plug in that number, we end up with 0 over 0 or infinity over infinity. Now, I didn't put plus or minus here, but that's true. It can be positive or negative, doesn't matter. If, when we plug in that number or approach infinity, we get a result of 0 over 0 or infinity over infinity, it actually turns out that the limit is the same whether we're dealing with the original function given to us, or it's the same if we actually take the derivative of the top and the derivative of the bottom. So feel free to pause if you want to write all that down. But as strange as that may seem at the moment, it actually makes our work a lot easier. Because I do want to make sure it's clear, we're not having to use the quotient rule. Quotient rule can take a little bit longer, for sure. Here, this is what we probably wish the quotient rule was. You just take the derivative of the top, all by itself. You just take the derivative of the bottom, all by itself. Then we'll try the limit again, and it interestingly gives the exact same result as the original. So here's our first example. We have the limit as x approaches 0. So think about it. Your first step should always be to just plug in the number, because there may be times, especially on the AP exam, when you have no idea if they're trying to use L'Hopital's rule or not. They're just going to say, solve this limit. Always just try plugging it in first. So I plug in 0, I get e to the 0, which is 1 minus 1. So I get 0 on top. I plug in 0 on the bottom. I get 0 on the bottom. So that tells us L'Hopital's rule will work. We want to make sure it works first. We get 0 over 0, so it does work. So our next step is to take the derivative of the top and the derivative of the bottom. The derivative of e to the x is itself. The derivative of negative 1 is 0. And the derivative of x is 1. So if you notice, this is the original. This is the derivative of the top over the derivative of the bottom. So now let's try plugging in 0 again. So if I plug in 0, I get e to the 0 over 1, which is 1 over 1. So my answer is 1. So all I had to do, as complicated as this equation might look, is take the derivative of the top, the derivative of the bottom, and plug in 0. And this is a limit we did not know how to solve before without using a calculator and using the table to figure it out. But now, with L'Hopital, you do. Okay, now this bottom one. This is one we could have done before using the dividing out, the factoring, and canceling out stuff, but you can see that there's another way to do it. So here it says the limit as x approaches 3. Well, if I plug in 3 on top, I get 0. 2 times 0. If I plug in 3 on the bottom, 3 squared is 9. 9 minus 9 is 0. So we get an indeterminate form again because it's 0 over 0 when we plug in the 3. So we know, based on L'Hopital's rule, if we have an indeterminate form, then the limit of the original is the same as the limit of the derivative of the top over the derivative of the bottom. Okay? So if it's easier to do this, you can distribute this. It's 2x minus 6. The derivative of 2x is 2. The derivative of 6 is 0, so you just get 2 on top. The derivative of x squared is 2x. So we've taken the derivative. Now we can just plug in the 3. 2 over 2 times 3 is 2 over 6, which reduces to 1/3. Feel free to pause this at any time if you need to take time to write this stuff down. Okay, so now we got one with trig. It says the limit as x approaches 0. So we have sine of x minus x. If I plug in 0, sine of 0 is 0, minus 0, still 0 on top. 0 squared on the bottom is 0, so it's indeterminate, 0 over 0. We are allowed to use L'Hopital's rule. Take the derivative of the top, which is cosine x minus 1, over the derivative of the bottom, which is 2x. But here we run into a new issue. if I plug 0 in, cosine of 0 is 1. So on top I get 1 minus 1, which is 0. If I plug in 0 on the bottom, I still get 0. So notice we took the derivative, but we're still getting an indeterminate form. We still get 0 over 0. The good news is we can just repeat the rule again. So L'Hopital's rule does allow us, if we need to, if we get an indeterminate form again, to just repeat the process by taking the derivative again. So, down here, I take the derivative of cosine x, that's negative sine x. The derivative of negative 1 is 0, so it goes away. The derivative of 2x is 2. So I've now taken the derivative twice. Now if I plug in 0, I get negative sine of 0 over 2. Sine of 0 is 0. 0 over 2 is 0. So there may be times where you have to take the derivative more than once to make it work. You can only do that if you get 0 over 0 again, or infinity over infinity, if that's what we're dealing with. So that's one trick you need to know about. There may be times you have to take the derivative more than once. Okay, this next one has a different trick you'll see in a moment. The limit as x approaches 0 of tangent x over 6x. Plug in 0, tangent of 0 is 0, 6 times 0 is 0. So it is an indeterminate form, 0 over 0. We take the derivative of the top, secant squared x, over the derivative of the bottom, which is 6. Now, if this is a calculator inactive question, you may say, okay, this is a problem. I have no idea what secant squared of 0 is. That's not even something you're required to memorize with the unit circle. That's fair. So if you have a calculator, you can just plug this in, but even then, secant is not a button or a calculator. Really, whether this is calculator active or not, you've got to remember what secant is equivalent to. Secant is the same as 1 over cosine, which means secant squared is the same as 1 over cosine squared. So I can rewrite this. This is the same thing. Secant squared of 0 over 6 is the same as 1 over 6 cosine squared of 0. Now this is something you do need to have memorized. Cosine of 0 is 1. 1 squared is 1. So 6 times 1 is what we get on the bottom for a final answer of 1/6. You do have to remember the stuff about trig. Got to remember secant is 1 over cosine. Cosecant is 1 over sine. Cotangent is 1 over tangent. Okay, those of you who like rules, here they are. I'll read through them, but again, feel free to hit pause if you need to. Our first step is to check to see that f over g is an indeterminate form at c of the type 0 over 0 or plus or minus infinity over plus or minus infinity. If it's not indeterminate, don't use L'Hopital's rule. L'Hopital's rule only works if we have an indeterminate form at the value we're approaching. If it is an indeterminate form, your second step is to differentiate f, differentiate g separately. Then you find the limit as x approaches c of f prime of x over g prime of x. But if, as we saw in the last slide, if f prime over g prime still gives you an indeterminate form at c, then you can repeat the process. Take the derivative of each one individually again, plug in c, see if that works. Okay, so now let's switch gears and look at ones where we're approaching infinity. So on this one, as x approaches infinity, well, as x approaches infinity, natural log is also going to approach infinity, or natural log of x will approach infinity. As x gets big, the top gets big. Okay, as x goes to infinity, x goes to infinity. So both the top and the bottom are going to infinity. That is an indeterminate form because we know they're both growing and growing forever and ever. So let's take the derivative of the top. The derivative of the natural log of x is 1 over x, and the derivative of x is 1. Well, 1 over x over 1 is just equal to 1 over x. So I didn't write that. Anyway, keep in mind this minus 1 really doesn't matter. Or over 1 is what I mean. This is really just 1 over x. So if you think about just this fraction, 1 stays the same, while the x is getting huge. So now you have 1 over infinity. And just like we talked about, that means the limit is 0. I meant to write 1 over x right here. Yeah, I'll do that. Hold on. Oh, over x. Okay. So 1 over x over 1 is the same as 1 over x. As x approaches infinity, the denominator gets huge. So this becomes things like 1 over 10, 1 over 100, 1 over 1,000, 1 over a million, 1 over a billion. That's getting tinier and tinier, so it's approaching 0. Okay, similar on this next one. The limit as x approaches negative infinity. So x is becoming larger and larger negative numbers. Well, as I plug it into x squared, that's going to approach positive infinity because the squared will make it all positive big numbers. And same issue here. If I'm plugging in negative numbers, that cancels out this negative in the exponent of e. So I'm going to get e to bigger and bigger numbers. So that's also going to infinity. So that shows this is an indeterminate form. So I'm allowed to use L'Hopital's rule, take the derivative of the top and the derivative of the bottom. Just remember, the derivative of e is itself e to the negative x times the derivative of the exponent, which would be negative 1. That's why I have that negative out front. Okay, so now, as x approaches negative infinity, the top is approaching negative infinity, and so is the bottom, because the negative infinity is canceling out with the negative there, but we have a negative out front, so we're still getting infinite over infinite. It's still indeterminate. That means we need to take the derivative again. The derivative of 2x is 2, and here, the derivative is itself, e to the negative x, times the derivative of negative 1, so that's why we switch back to a positive. So now the top is staying 2, not changing, while the bottom is going toward infinity. Anytime the top stays the same and the bottom gets huge, the whole limit is going toward 0. Okay, so you can tell these two examples I have here are different because they're not fractions. Now, in another calculus class, you may just leave them like this and then still solve them using some other methods, but we're going to stick with just the indeterminate forms we know, which are 0 over 0 or infinity over infinity, meaning we want fractions. So if you're given something like this, you need to think, okay, how can I rewrite this as a fraction? So this one, hopefully it's not too hard to figure out. Since we have a negative exponent, we can move that to the bottom, just like that. Now we have a fraction. As x approaches infinity, the top is going to infinity, and so is the bottom. So we use L'Hopital's rule, take the derivative of the top and the derivative of the bottom. Sorry, trying to move that out of the way. There we go. So the derivative of e to the x is itself. Here we had to multiply by the exponent and subtract 1 from the exponent. Now it may be a little hard to figure out what's happening to the denominator because of the negative exponent. So whenever you get negative exponents, I would recommend you rewrite it by pulling that term to the top. So I'm not taking a derivative or changing anything here, I'm just rewriting it. Because having an x to the negative 1/2 on the bottom is the same as having x to the positive 1/2 on top. Because now we can say, okay, if x is approaching infinity, the top is going to infinity. It's getting huge, while the bottom is just staying 1/2. So this is the reverse from the two we saw on the last slide. Here, the top is going to infinity. The bottom is staying the same. When the top is what's growing huge and the bottom is staying the same, then our limit is infinity. So infinity over a constant is infinity. Back here, though, we saw a constant over infinity equals 0. A constant over infinity equals 0. Okay. So this example may not be as obvious at first how to rewrite this as a fraction. I mean, you could put x to the negative 3 on the bottom, but then you're actually not going to be approaching infinity over infinity, or 0 over 0. So it's better to remember those trig things I was talking about. You got to remember what cotangent x is equivalent to. Cotangent is equivalent to 1 over tangent. So again, I've not used L'Hopital going from this step to this step. I've just rewritten the exact same thing. Cotangent is the same as 1 over tangent x. And now I'm in that fraction form, which is what we know we need to check on in order to use L'Hopital's rule. If I plug in 0, I get 0 cubed, which is 0, over tangent of 0, which is 0. So this is an indeterminate form, which means we can use L'Hopital's rule. So I take the derivative of the top, get 3x squared, take the derivative of the bottom, and I get tangent x. So now we try to plug in 0. But again, you may have a problem because you don't know what secant of 0 is equal to. So just like we did before, you have to remember secant is the same as 1 over cosine. So secant squared on the bottom is the same as having cosine squared on top. So if we wanted to, just to make it sure it's clear, we've moved secant squared from the bottom to make it cosine squared on top. So these are equivalent. There's no derivative that's happened here. We're just using the trig properties, or trig identities would be the right word, knowing secant squared is the same as 1 over cosine squared, which flips it up to the top. So now if I plug in 0, I get 3 times 0 squared times cosine squared of 0. Well, as soon as you see 0 squared right there, we're multiplying, so that's all going to go to 0. So our limit is 0. Okay, if you're in my class, there's your homework. Make sure you note the instructions on 7 through 16. I'm saying ignore what they say and just find the limit as x approaches c. Good luck.